Our next speaker is Beáta Faller, and her title is Distribution of Phylogenetic Diversity Under Random Extinction.
Thank you. So I have been doing my PhD with Charles Semple and Mike Steele at the University of Canterbury since February. You can see my supervisors here. I'm working on problems that are related to the so-called phylogenetic diversity, which is a measure for describing how much of an evolutionary tree is spanned by a subset of species. I'm particularly interested in problems that are related to combinatorics, computational complexity algorithms, probability theory, also simulations. In my talk, I will present joint work with Mike Steele and Fabio Pardi. The talk will discuss the distribution of phylogenetic diversity under random extinction. I would like to start with introducing the probabilistic model under consideration, and let's start with the notion of phylogenetic diversity. So we have a set of present species. We denote this set by X, and we also have, of course, a rooted phylogenetic X tree tau, which represents the evolutionary development of these taxa from their common ancestor. In my figure, present species are denoted by colored circles. We have also lengths on the edges. There is a map, lambda, that assigns a non-negative length lambda e to each edge e. Such a length does not necessarily refer to the temporal duration of the development on that edge, but rather it represents something like the amount of the genetic change on that edge, or perhaps other features, morphological diversity, if you like. If we consider now a subset x prime of x, then the phylogenetic diversity, or briefly the PD score of that subset, is the sum of the length of the edges of the minimal subtree that connects this subset and the root vertex. The figure shows the situation where this subset consists of two species, the blue and the green one, and the PD score of that subset is the sum of the lengths lambda A, lambda B, lambda D, and so on, because these are the lengths of the edges of the minimal subtree connecting the blue and the green species and the vertex root.
Not quite.
Why?
I would say D and C rather than D and A.
Sorry, could you please repeat it?
Blue to the green, if I see correctly. We go H, F, C, and D.
Yes, but I said which the minimal subtree that connects the subset and the root vertex.
I always have the root.
Yeah, in that case we have always included that. Okay, and these edges are indicated by the colored edges in the figure. In the field of bullets model, we have a map P that assigns to the taxon I a survivor probability Pi. We construct a random subset x prime by assigning each element of x to x prime independently with its survivor probability. For example, the taxon I will be an element in x prime with probability Pi. We regard x prime as the set of taxa that will still exist at some time in the future. We have two models. The simple field of bullets model, where each species has the same probability of surviving, whereas the generalized field of bullets model allows each species to have its own survivor probability. Extinction events are in both models treated as independent events. Under the field of bullets model, we define the future phylogenetic diversity as the random variable, which is the phylogenetic diversity of the random future subset x prime. Let phi denote this random variable. The figure shows the situation where the random future subset consists of the blue and the green species, and as we have seen, the PD score of that subset is the sum of the lengths of the colored edges. So we see that there are edges that we sort of count and other edges that we don't count, and it can be seen easily that phi can be written as the sum of the terms lambda e times ye, where again lambda e is the length of edge e, and ye is a binary random variable which takes the value 1 if we count the edge e. That is, if e lies on at least one path from the root to one of the elements of x prime, and which, so lambda ye takes the value 0 otherwise if we don't count the edge e. Okay, so this is the model we set out to study, and imagine now a sequence of such models, a sequence of trees of increasing size, each tree having its edge length function and its survivor probability function. And consider the corresponding sequence of the future phylogenetic diversities. Our goal was to determine the distribution of phi along these sequences as the size of the trees goes to infinity. Okay, but let's forget about the asymptotic behavior and these sequences for a while, and let's start with the mean and variance. Okay, so since the formula for phi includes the random variable ye, which is just a binary random variable with expectation that which is the probability that ye takes the value 1, we get a simple formula for the expectation. We denote the probability that ye has value 1 by PE. The variance is also quite easy to compute. It includes a sum over all edges in the tree, and another one which is a sum over ordered edge pairs, EF, such that E and F are distinct edges, and the path from the root to the edge F includes somewhere the edge E. Equivalently, we could say that the taxon set below F is a proper subset of the taxon set below E. Okay, so we know how to determine the two main parameters of phi, and we have seen that phi is sum of many random variables, and this suggests that phi might be normally distributed. It turns out that under two mild conditions, phi has asymptotically a normal distribution even under the general model. The first condition is that the survivor probabilities are not too extreme. That is, most of them are neither arbitrarily close to 0 nor arbitrarily close to 1. And the second condition is that the pendant edges on average are not too short in relation to the largest edge length in the tree. Pendant edges are edges that are incident with a leaf. Of course, these conditions can be formulated in a mathematically precise way. Okay, one question one could ask, does the condition hold if we drop one of the or both conditions? The answer is no. To see why we can't remove completely the first condition, consider the situation where all species have survival probability 0 or 1. In that case, C1, the first condition fails, and since this situation leads to a degenerate distribution, it's clear that we can't remove the first condition completely. For the second condition, consider the tree in the figure with n leaves. The leaves are labeled from 1 to n. This tree has n-1 pendant edges of size 1 over the square root of n-1 and 2 another edges that have length 1. Consider now the sequence of such trees of increasing size, and in particular consider the corresponding future phylogenetic diversities. We assume one more thing, namely that survival probabilities are the same, so each species has the same probability of surviving, and this value is strictly between 0 and 1. It can be seen that the sequence of the random variables does not converge to the normal distribution. And since in this example the first condition is satisfied but the second one fails, we see that the second condition can't be dropped completely either. Okay, and why was it not trivial to prove? Well, it's because phi is not sum of identically distributed random variables, and more importantly, the terms in the summation are also not independent. You will understand this if you have a look at the figure where you can see a situation for such a dependency. Y, E, and Y, F are not independent. We see that the survival of any taxon below F implies the survival of a taxon below E. Okay, and we have also independent variables. This would be something like this. Okay. So we see that the usual central limit theorem does not apply in our case. Now I will show a very brief outline of the proof. Mike came up with the basic idea, namely to decompose the tree by partitioning the edge set into two classes. The first class includes edges that are close to the root, and so they separate the root from enough species, enough leaves, so that we can be almost certain that at least one of these species will survive. These edges have more than f of n species below them, where n is the number of the leaves in the tree, and the function f depends also on the conditions C1 and C2. Edges in the second class are included in pendant subtrees, and they have only at most fn leaves below them. Let phi1 denote the contribution of the central edges to phi, and phi2 the contribution of the edges in the pendant subtrees to phi. Okay, just very briefly the three main steps. It can be seen that phi1, the contribution of the central core, converges in probability to a fixed function of n, which is non-random. Secondly, the contribution of the pendant subtrees are independent, and so we can apply a version of the central limit theorem for double arrays of variables to see that phi 2 is asymptotically normal. Finally, we can combine these two results and use Slutsky's theorem to achieve that phi is asymptotically normal as required. Okay, the theorem has also a few useful consequences. Firstly, if we want to compute the distribution of phi, we only need to determine its mean and variance, and we have seen that this can be done easily. We also may wish to predict the probability of a worst-case situation, a probability of the situation that the future phylogenetic diversity is less than some critical lower limit A0. We can do it by estimating this probability using a normal distribution. And if we know these probabilities, then we can design strategies to minimize them. Also, if we want to apply the result for Huel trees, we can do that because the conditions apply for these trees. Let's see what is left to do. Sorry, it's something else. What do we know? We know that there is a polynomial time algorithm for calculating the exact distribution of phi. Fabio came up with an algorithm. And another thing is that we can extend the result for a modified version of phi on unrooted trees. Okay, and now what is left to do? One thing is that exploring models that weaken the assumption that taxon extinction events are independent would be interesting, and it would be great to simulate the distribution of phi and compare the results with the theoretical result. Finally, there is something else. It is a bit different problem, but it's still PD related. I'm currently very interested in a problem. This is optimizing PD with ecological constraints, where we have a food web, and this is joint work with Charles Semple and Magnus Bordewijk. Okay, and finally I would like to thank Mike, Fabio, Charles and Magnus for the collaborations, the Alan Wilson Center and the University of Canterbury for their support, and for you for listening to me. Thank you.
Are there any questions? No questions? All right, well, let's thank the speaker again.
Thank you.
That's all.